Okay, here we go with inverse trig relations. We are going to be exploring relations and inverse relations with regard to trig, but we need to review what a relation is first of all, really quickly. So a relation, remember, is just a set of ordered pairs. So like you have this relation Q, and if we wanted to figure out the inverse relation, all we're going to do is interchange our elements. So the x's become y's, and the y's become x's. So we end up getting Q inverse is this relation. And remember, sometimes relations are functions, and sometimes they're not. So we do make that distinction when we need to. But everything that we're going to be talking about right now is going to be considered a relation. And we're not going to focus so much on if it's a function or not. So we had some problems in the past where we had to figure out what the inverse of a relation was, and they gave you the equation for your relation, and then they asked you what is the inverse. And if you recall, what we had to do is we would take our equation and we would change the x and y. So the y would become an x and the x would become a y. So we switch x and y, and then we would solve for y and go through the steps, and we get this equation. So this ends up being the inverse of that equation. Now it asked us to graph the function and its inverse on the same coordinate plane. And hopefully you guys recognize that these are both lines. So here's our coordinate plane, and if I were to graph this first equation, we get this line. And maybe you even recall that the inverse and the original graph should be symmetric about this special line, y equals x. We call that the mirror. And if we were to graph the other line, there we go, you can see how if we folded along this y equals x, all the points on the red line would end up landing on the blue line. So specifically, you can see that this point here lands right there. Okay, this point here is going to land right there. And you can see where the two lines intersect each other should intersect your y equals x line. Okay, so this is with lines. So how would this relate to trig? Let's take a look. If we had to graph y equals cosine x and its inverse on the same axes, first of all, I don't want you to panic. We're not going to be graphing in this unit. I just want you to see what these graphs look like. So first of all, we go through the process of switching x and y. So y equals cosine x becomes x equals cosine y. If you recall from graphing unit, these are all the main points, the max and mins and zeros for cosine. And if we were to graph that on this coordinate plane here that we have, it would end up looking like that. Now it's a little interesting to note here, the y-axis is not labeled in integers, it's labeled in radians. But if we wanted to see where 1 is, because that's a point on our graph, if you think about pi is 3.14. If we divide that by 2, this is a little bit more than 1. So 1 is going to be a little bit less than it. Okay, sorry, I got interrupted there, so I pushed pause, and I have no idea where I was in my explanation. So if I'm repeating myself, I apologize. So we figured out where 1 is based off of the 3.14 divided by 2, this being a little less than that. Okay, so now let's graph the inverse of cosine, this x equals cosine y. If I take these points and interchange them so the x's become y's and y's become x's, these are now the new points for my new graph. And if you look, when we go to graph it, isn't that interesting? Now it snakes its way along the y-axis instead of along the x-axis. And here's our mirror, that when they get reflected, you should see all these points match up, the red and the blue graphs. Pretty cool, right? Not that you have to graph it yourself, but it's just interesting to take a look at. All right, so what happens is we have this equation of x equals cosine y. And when we want to talk about an equation, we typically like to have it in the y equals format. So what they did is when you take x equals cosine y and you solve for y, we created a new notation, if you will, and we call that arc cosine. So this x equals cosine y is the same as y equals arc cosine x. And what this actually means is y is an angle whose cosine is x. And you're actually familiar with this already because we are used to looking at this in that notation with the cosine inverse, with the little -1 exponent. And you guys have been doing this since Unit 1 and with law of sines, law of cosines, right? It's just a new notation. So these two things, in essence, mean the same thing. So if we read this off, we're saying we want to find the angle y, that when we take the cosine of it, we get root 2 over 2. So where is cosine going to be root 2 over 2? And you'd figure out that angle. And the thing is that these problems you're not going to be using your calculator for. You're going to be using your unit circle on. Okay? So you would look at your unit circle and figure out where cosine is root 2 over 2. All right, well, we are going to make sure that we do all of these in radians, not degrees. So let's take a look at this first example here. It says y equals arc cosine of negative root 2 over 2. So if you have your unit circle, pull it out, take a look at it, and look at where cosine is negative root 2 over 2. So first of all, think about which two quadrants is cosine going to be negative in. That should be the second and the third quadrant, right? So it should be here and there. So when you're looking at your unit circle, these two angles are going to be 3 pi over 4 and 5 pi over 4. So those are your two answers. Let's try another one. What about arc sine of positive root 2 over 2? So that's the sine inverse, right? So where is sine positive? Well, sine is positive in the first and second quadrants. And when you look at your unit circle, looking at sine, root 2 over 2 here is going to be pi over 4, and there is going to be 3 pi over 4. Not too bad, right? It's pretty easy stuff. Okay, so then you have to think about, are there any more answers that satisfy these equations? Well, of course there are. All right, so let's think about this. Remember in Unit 1 where we had rotations. We could rotate around. We could take our ray and rotate around a couple times, 3 times, 4 times, in whichever direction. Maybe we wanted to go this way. And then we still ended up here. And if you got that new angle measurement and you took the cosine of it, you still got negative root 2 over 2. Well, what we can do is we can add 2 pi to each of these answers, and we get 2 more answers, 11 pi over 4 and 13 pi over 4. Well, what if I went the opposite direction? What if I subtracted 2 pi? What if I rotated 3 times around, and then it would be 6 pi? How many answers do you think we could possibly get? In fact, there's infinite number of answers. So how would you list out every single answer? We definitely are not going to write them out individually. What we're going to do is use set builder notation. So set builder notation is a very specific way of writing your answer when you have to write a set of numbers. So it's like an infinite set of numbers is your answer. So what you do is you start off with your fancy braces. So make sure you've practiced how to write those. We talk about the variable that we're solving for, so y. The colon is read as such that. So we're finding all y's such that, and we put our first answer. Y equals 3 pi over 4. But then we add 2 pi times n. And n represents how many rotations we're doing. So if we have 1 rotation, n is 1. If there's 3 rotations, n is 3. If we have 2 negative rotations, n is negative 2. Okay, so there's one answer. But we had a second answer, right? We had 5 pi over 4. So we have to say, or y could equal 5 pi over 4 plus 2 pi n. Now, within these two answers, we've introduced a new variable, and that new variable is n. And we need to let the reader know, what does n represent? Well, we're talking about full and complete rotations that are either positive or negative. So n is going to be an integer. So we have to say n is in the set, or is an element of, the set of integers. Remember, I represents integers. And then you close your little braces. So this is how you would write your answer in set builder notation. Okay, so let's try a couple of examples. What is y equals arc cosine of negative root 3 over 2? So you should look at your unit circle and find where negative root 3 over 2 is for your cosine. So that's going to be in the second and the third quadrants. And hopefully you came up with 5 pi over 6 and 7 pi over 6. But then we needed to put that into set builder notation. So this is what it would look like. Remember the y such that y equals 5 pi over 6 plus 2 pi n, or y equals 7 pi over 6 plus 2 pi n. But then don't forget to write your n is in the set of integers. Now, so far we've only been doing arc cosine and arc sine, but we can do arc tangent, arc cotangent, arc secant, arc cosecant. We can do it for any of our 6 trig functions. So what if we did y equals arc tangent of root 3? Well, tangent, let's see, if it's positive, it's going to be in the first and the third quadrants. And if it's root 3, then that means we're going to be at pi over 3 and 4 pi over 3. Now the interesting thing is with tangent, when you get your two angles, they should be directly opposite each other. They're exactly pi units apart, pi radians away from each other. So if I took pi over 3 and added pi, I should get all the way down here to 4 pi over 3. So what you can do, and this is actually really nice and sweet, is that instead of taking pi over 3 and adding 2 pi n, and then taking 4 pi over 3 and adding 2 pi n, I only have to take the first one and add pi n instead of 2 pi n. So I'm adding pi every time. So here I add pi, I get down here. If I add 2 pi, I get back up here. Add 3 pi, I'm down here. Add 4 pi, I'm back up there. So this is a nice, simpler way of writing your answer, and you can do that whenever you're doing the arc tangent or arc cotangent, because those answers should be directly opposite each other. They're either both positive or they're both negative. Okay, and think about it. What was the period of tangent and cotangent? It was pi, right? And the period of cosine and sine was 2 pi. So you can make that connection too. All right, so there you have it. Hopefully that wasn't too long and in-depth and hurt your brain or anything. That's it.